Hi everyone. We've been talking about telescopes and different types, how they use light energy or invisible radio wave energy in order to interpret and analyze the things that are happening out in space that we're not able to see with our own eyes. And we call that energy wave electromagnetic energy. So, what are these waves? Well, they're just disturbances that transfer energy through space and matter. So, energy waves can be transferred through the earth during an earthquake. It can also be transferred through water, those are the waves that we see. Sometimes you're going to see electromagnetic energy abbreviated as EME. It's just such an easier way to write all those letters. So let's look at some properties of these waves. The highest point on a wave is called the crest. The lowest point on the wave is called a trough. Not only do we have the locations of the highest points and the lowest points, but we use those to measure the wavelength. It's the distance between two crests or two troughs that are next to each other. It measures one complete wave. Notice I have two different locations. I have a wavelength between two troughs. It starts here, goes all the way up, and back down to its lowest point. That is one complete wave. Here I look at the wavelength between two crests. It goes down to the trough and all the way back up. So that is the wavelength. It's just the easiest when looking at two crests next to each other or two troughs. But there are other ways you can do it. We'll just worry about crest to crest and trough to trough. We like it easy. Another property of waves is the amplitude, and it's the maximum height of a wave measured from the resting point or equilibrium. So rest point or equilibrium, it's the point in a wave where if it had no energy, where it would be hanging out. Now, that's not real. All waves have energy. It's just their definition. But if they were to have no energy, that is where we would find it. So when we're looking at these waves transferring energy, there's another vocab term. It's called the frequency. So the frequency of a wave is the number of complete waves that pass a specific point, usually the rest point, in 1 second. If the waves are very close together, they have a high frequency. This is a little bit of a trick. And if the waves are really far apart, it has a low frequency. Because think about it. A high frequency means it's happening very, very, very frequently. So there's a lot of stuff moving past there in a very short amount of time. But if you have a low frequency, it's not happening as often. I think of a low frequency like a lazy day on the beach. The waves really aren't moving, they're just kind of hanging out. Where when you have a high intensity day at the beach with all those waves, there's one coming in after another. It's constant. So maybe that's a little trick to help you think of high frequency versus low frequency. And we use a measurement called hertz, capital H, lowercase z. No, it's not the car rental company. It's an actual unit of measurement. It's waves per second is another way to have the units. All right, so now that we know a little bit about the properties of electromagnetic energy, let's look at the application. We call this the electromagnetic spectrum. Now you may see that as EMS because we like shortcuts. It's just the complete range of frequencies of electromagnetic waves known as the electromagnetic spectrum. You can see here on the right, we have a diagram showing the full range of all the different waves and their energies. And we can use these different frequencies to help gather information about distant objects. So stars, galaxies, nebulas, planets, anything that it's really giving off some kind of energy, we're able to interpret. And depending upon the type of energy it's giving off, that would determine the satellite that it's being interpreted by. Let's watch this short video clip before we start to talk about it even more.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
So let's delve a little further into the electromagnetic spectrum. There were quite a few vocab terms that they used in there. They talked about wavelength, frequency, energy. So, looking at each of the different types of electromagnetic energy, first is radio waves, and these have the longest wavelength. Because they have the longest wavelength, they have the lowest frequency and therefore the lowest energy. So a long wavelength means it takes a long time for, the waves to cycle through. That's your lazy day on the beach. So some practical examples of radio waves is an FM AM radio station, not the same thing as satellite radio, but just a regular radio station in the car. Radar guns that they use for tracking people that are speeding, or not just people speeding, but a baseball pitch, how fast that's going. Those all use radio waves. And stars give off radio waves, which we know because there are those radio telescopes. Next, we have microwaves. And microwaves are really like the principal carrier of data transmission within our Earth system. If we didn't have microwaves, we wouldn't even be having this conversation through the computer right now. So some examples are, surprise, the microwave box in your house. It uses those microwaves. Wi-Fi routers, cell phones, and as we just saw in that short video clip, stars also give off microwaves. And we're going to talk a little bit about that in more detail in a later unit. Next, we have infrared waves. And these are just below visible light, meaning there's a little less energy, and that prefix infra just means below. So it's below visible light, specifically red light, which we'll talk about in a minute. So some examples of infrared waves, remote controls, flames, lamps, night vision goggles, and surprise, stars also give off infrared waves. Now, the type of electromagnetic energy that we're most familiar with is visible light. When I say the term light, that's what you think of. But in actuality, all electromagnetic energy on the electromagnetic spectrum can be called light. Think about that. All of these 7 types of energy waves are all called light. Visible light is the only wavelength that we can see with the human eye. When we are looking out on a nice sunny, cloudy, rainy day, it doesn't matter, we cannot see the microwaves that are moving through the air. We cannot see the X-rays moving through the air. We can only see the visible light. Visible light consists of Roy G. Biv. You may remember this from elementary school. It's the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. Make a rainbow. Sorry, that's one of Watson's TV shows that he loves right now. So Roy G. Biv is all the colors of visible light, the main colors, and they go from lowest to highest energy. So red has the lowest energy, the longest wavelength, the lowest frequency, and violet is actually the more high energy wave. So some examples, things that we know, light bulbs, fires, surprise, stars also give off visible light. Now let's get into a little bit more high energy. Then we have ultraviolet light. This is also called black light. So if you ever have a black light that you're using, it is typically an ultraviolet light. So some examples. Sterilization. So after you go to the dentist office and you get your teeth cleaned, nice and pearly white, they sterilize the tools that they use so that there's no germs or bacteria that transfer from one patient to another. Stars also give off UV light. This is the light from the sun that causes sunburn. It is a little bit more high energy, and our skin cells really don't like it, so it can cause that sunburn. In haunted houses, using that UV light. Even more high energy are X-rays, and they're high frequency waves with a lot of practical purposes. So we use X-rays to see inside organisms, and mostly if there's a broken bone, you probably have had a X-ray of that. In some objects, when we had discovered over in the Eastern civilization, we had learned that there were mummy tombs and sarcophaguses, and we wanted to see inside of it. We used X-rays to view what was inside. Airport security, when you are going through TSA lines, and even when you're checking your bag, they will run it through a X-ray scanner to see if you have any contraband. And surprise, stars also give off X-rays. Lastly, we have gamma rays, and these have the shortest wavelength, the highest frequency, and the highest energy. It's a very short wavelength. It's a very short time span for each wave to come. That's our high energy wave at the beach. So what are some examples of gamma rays? Well, radiation therapy that cancer patients sometimes receive. Again, sterilization, just like with our UV rays. And surprise again, stars also give off gamma rays. So the electromagnetic spectrum and electromagnetic energy have a lot of purposes. We notice that stars pretty much give off all of these rays. So let's look at electromagnetic energy and different telescopes. So we know that the way that astronomers observe light really depends on the portion of the spectrum that they are looking to study. So we can see in this diagram that different detectors are sensitive to different wavelengths of light. Remember, when I say the word light, I mean the entire electromagnetic spectrum, not just the stuff that we can see. So over here, we have our longer radio waves where we're using our radio satellites. We then have different satellites above the atmosphere because not all of them can actually go through the atmosphere. Then we have observatories that are here on Earth where we can look at just optical telescopes where we can look at just visible light. So, as I just said, not all light can get through the Earth's atmosphere. So for some wavelengths, we have to use those kind of telescopes and other instruments on the satellite.